Hello and welcome to this video on the basics of electricity as part of the electrochemistry topic. So one of the most fundamental things that we need to understand about electric circuits and electricity is this idea of potential difference here. So quite simply, potential difference arises when you've got a situation where you've got two areas of different charge. So if we have positive charges up here and negative charges here, we know there's going to be a tendency for them to become attracted to each other. So if, for example, I just focus in here on this positive charge up here, and I attempt to move this positive charge further away from the negative charge, I need to do some work. So a bit like trying to push a boulder up a hill, I'm going to need to input some work in order to be able to get, I need to input some energy in order to get that positive charge further away. However, if I allow the positive charge to go a little bit closer to the negative charge, then some of the energy that's stored here is going to be converted. So energy is going to be converted to kinetic energy as the charge moves. So the key point here is that we have energy stored by separating charges. And that's known as electrical potential energy. So we can think about this top stage here as having a higher electrical potential energy. Let me try and draw that a little bit more vertically. So this stage here, if we think about this as being the energy, then this state here has got a higher energy, and this state here would have a lower energy. So we've got a potential energy difference between these two. So the difference in potential energy we can just represent by an arrow there. So in order to be able to move a positive charge, if we put another one here, let's say, up to this point here, we need to input this amount of energy. So, sorry, the positive charge put on there. In order to be able to move that up, we need to input this much energy. Now, clearly the amount of energy we need is going to depend on the size of the charge. So as we don't really want to have to worry about that, it's convenient to have a measurement which isn't in terms of energy, but is actually in terms of something called potential. So if we, instead of measuring here the energy, we measure the potential, which is the energy divided by the charge, then it doesn't matter what size of this charge is, we just get a measurement of the energy needed per 1 coulomb of charge. So this here is now the potential difference. And measured in volts, so sometimes known as a voltage, and that is the difference in energy between these two states for 1 coulomb of charge. Now this slide is just to show that it's possible to have potential differences between two states of the same charge. So for example, if you had a region on a conductor like a metal which had a very low amount of electrons in, then it would be like this point here. And if you had a region with a very high concentration of electrons, it would be like this point here. And the point is, this one will be a more positive potential because there's less negative charge. So there's no higher potential. And this one here will be a more negative, or a lower potential. So we still, in this situation here, would have a potential difference. So if we're measuring our potential difference, V, then we're going to have a lower potential and a higher potential state. So there's still a potential difference here. So remember, that's energy is stored even in this situation. Now, what use is that energy? So we think about how this potential difference affects circuits. And in order to do that, I'm just going to use this simulation, freely available simulation called FET. And so we've got here a battery or a cell, and that's got a positive end in black and a negative end in grey. And essentially, you can think about this as just a source of energy. So as long as we have a route for the electrons that are the charge carriers here in order to be able to flow, so we'll put a few wires in here, which we can get a current flowing around here. And a current is just a movement of charged particles. In this case, for metal wires, they're electrons. And you can see that the electrons are flowing around from the negative end to the positive end because they're being attracted by the opposite charge. Now, this is all well and good, but actually what we want to do is something useful here. So what we can do is put in something like a light bulb, which just connects up the circuit, and then the light bulb will start to shine. You could put here your phone charger or your laptop, and we can start to do something useful with the energy that's stored by separating these positive and negative charges. And that current is going to depend on the size, the amount of energy, the potential difference here. So for example, if I change the potential difference of the voltage on this battery down to 4.5 volts, you can see that the charge is moving more slowly, so the current is lower. And it's also going to be affected by the size of the resistance to the flow of charge, which is in the bulb. So if we change the resistance of the bulb down to, say, 5 ohms, then now you see that the bulb is showing brighter because the current is flowing faster. Now, how do we actually practically know what the size of the potential difference is here? Here I've just been able to set it because it's a simulation. But in practice, we use a tool called a voltmeter, and essentially this it has 2 terminals, and whichever 2 points on the circuit you place the terminals over, it tells you the potential difference between them. So if we do that here over the cell, we find that it's actually 2.25 volts when we'd actually set the voltage here to 4.5. So it's not actually giving us the true potential difference across the cell, which is known as the electromotive force of the cell. Now, in order to be able to get this, what we need to do is make sure that there's no current flowing, because whilst there's a current flowing, the potential difference will be distributed over the different components in the circuit, and so we want to make sure that it's entirely across the cell. And so what we can do is split this circuit, and when we've got no current flowing, we're measuring the true electromotive force, the EMF, of the cell. So to summarize that, potential difference is a difference in charge between 2 places. So imagine we have negatives there and a couple of negatives here. This is going to be the more positive, and this is going to be the more negative. And that's exactly what a cell is doing if I just use a different color just to highlight. So this would be the negative end, and this would be the positive. And that could well be the type of situation you're getting in an electrochemical cell. The more positive a region, this is higher potential, so this one's higher, and this one would be lower. Potential difference between the terminals acts as a source of energy to move charges around a circuit, and that movement is called current. And the potential difference generated by a cell is known as its electromotive force, or EMF, and this can be measured with a voltmeter. Typically, EMF is given a symbol either with a Greek letter, an epsilon, or just E in the context of electrochemical cells.